And here we go. Okay. So guys, let me sort of lay out for you the day today, because there is the possibility that this is going to lull you not to sleep, but into complacency. So guys, what's going to happen is we're going to talk about all the fundamentals that you need to understand about acids and bases. This is going to start with a whole lot of review from last year. We're going to talk about Arrhenius acids and bases. We're going to talk about Bronsted-Lowry acids and bases. We're going to talk about conjugate acids and bases. We're going to talk about pH. And guys, you learned all of that last year. But the problem is if you start thinking, I knew this, I know this, I know this, I knew this, I know all of this, I don't need to know this because I know it, then the problem is when this switches, when we start talking about what is called the autoionization of water, you're going to go, oh wait, I don't know this, and I haven't been paying attention because I thought I knew all of this, and now I don't know what I'm supposed to know because I haven't been listening because I thought I knew it all. You know what I'm saying? So guys, the trick is ask questions as we get into this initially, because you may not remember all the details with conjugates and things like that. But then guys, when that transition happens and we talk about the autoionization of water, I'm going to try to draw your attention to it, and guys go just, hey, be careful because this is new. But if you miss it, it could back up on you. So guys, acids and bases. First thing we need to know is definitions. The definitions are named after the chemists that proposed them. And guys, the first one that you need to know is the Arrhenius definition for acids and bases. You guys remember? Or should we go? You don't remember, do you? No. Be careful, because protons is Bronsted-Lowry. So that's not, let me just give it to you. Guys, an Arrhenius acid is defined as a substance that increases hydrogen ion concentration when it's dissolved in water. Now guys, is that true? Do acids do that? Yes. But what you're going to find out is that this definition is too narrow. So we're not going to, well, let me say it to you differently, and maybe this will make sense. Guys, the only time the Arrhenius definition really works well is when we're dealing with strong acids and bases. It doesn't do a good job of including weak acids and bases, and therefore we need to expand on it. But before we can expand on it, let's talk about bases. So guys, in the Arrhenius way of thinking, bases are substances that increase the concentration of hydroxide in solution. And so guys, this works fairly well. Functionally, this is a good functional definition. Yes, acids make hydrogen ion go up. Yes, bases make hydroxide ion go up. But the problem is that while this is functionally good, it's also too limiting. And so what we're going to do is while we'll keep this sort of in the back of our minds, it is not the definition for acids and bases that's going to inform our understandings throughout the year. So what we're going to use is the Bronsted-Lowry definition. I was very excited when I figured out how to do the little line through the O in Bronsted. It was a significant moment for me. Oh, but it's actually its own character. Right. And when I figured out...
I was like... I was really excited when I figured out
But the thing that was especially meaningful is the year that I figured this out, I had a student whose name was Soren, and his name had the S-O-R-E-N, had the slash through it. We bonded. It was nice. So guys, definitions in the Bronsted-Lowry sense. Acids. Super simple, but we'll make the connection. Ready? Bronsted-Lowry said this: acids are proton donors. So guys, maybe what we can do is freeform here for a minute and talk about this. So guys, how does this line up with this? Not basically, they are the same. Guys, do we need to talk about that, or can we just say that that's true? These are actually saying the same thing. Because guys, hydrogen ions are protons, right? Do we need to talk about that, or can we just take that that's the case? Okay, so guys, the Bronsted-Lowry definition and the Arrhenius definition for acids are the same because hydrogen ions are protons. But now let's look at the base definition. The base definition is where we need to talk about a little bit more chemistry. So guys, the base definition in the Bronsted-Lowry sense is that bases are proton acceptors. So again, we need to have this thought. How does that support or undermine the Arrhenius definition for bases? Is it complementary? Is it contradictory? How do these things fit together? Are you leaving? Nice. Okay. The struggle is real. So guys, let's get, because this is an important thought. You got to make sure this is new. How do these support? Do they contradict? What's the connection?
So, like it supports it in the sense that like a hydroxide ion can be a proton acceptor. But when there are other things that aren't strictly hydroxide acceptor.
Okay, and I would agree with that. But are you saying that it is then contradictory in some cases and supplementary in others? I think we could even take it a step further and say that it's always complementary. But guys, and this is a deep thought, and let me just tell you right now, I'm going to take you somewhere really weird right now. But guys, the weird that we are about to touch on is the weird that makes acid-base chemistry funky. So guys, let's pull this together in our heads. Arrhenius definition, what do acids do? Give away protons. What do bases do? Give away OHs. But guys, now in the Bronsted-Lowry definition, we're saying acids give away protons and bases take them in. And guys, what we're going to find out in a minute is that these two ideas are always complementary, but they are always complementary in only one context. And the context is the important part. Say it again. And what does aqueous mean? In water. Guys, if you're sort of taking notes the way I am, the thing you've got to understand is water is the connecting link between these two definitions. And guys, this is where this gets a little bit wacky. So once you've got this written down, we just need to get this out on the table. Ready? So follow this thinking. What do acids do? Give away hydrogens. What do bases do? Give away hydroxides. What is water made of? Hydrogen and hydroxide. So guys, what is water? Is it an acid or is it a base? It's both. And guys, here's the thing that makes this really interesting. All of the acid-base chemistry that we are going to do will always be in water. So the analogy that I use is this. Imagine that you're a kid playing on a playground and you're playing a game, whether it's ball or swing or catch or whatever, but you're playing on the playground. But guys, the playground is not part of the game. It's just where the game happens, right? Well, guys, unfortunately, when you're doing acid-base chemistry, the playground gets involved in the game. because all of this chemistry happens in water. So you can't just think of acid-base reactions as being an acid reacting with a base completely separated from its environment, because that is not the case. When we do acid-base chemistry, it's always in water, and water, the playground, gets involved in the game because water is an acid and a base. And so guys, you're going to find, and this is one of the things that makes this unit tricky, is sometimes we will think about the water as being involved in the chemistry. And other times we won't think about the water as being involved in the chemistry. And it's one of the tricky bits is you're going to have to figure out, when do we include the water and when do we not include the water? So now let's talk. So guys, let's go down here to the Bronsted-Lowry definition and let's talk about what it means to accept protons. So guys, do this with me. Say that you've got some substance that is a base. So just write down a B. Doesn't matter what that base is. But guys, that base is in water. So that base will react with the water that it's in. And when that base reacts with the water that it's in, what does Bronsted-Lowry say bases do? Look at the definition. What does it do? Takes in a proton. So guys, when this takes in a proton, it forms BH+. So the base takes in the proton and it forms this. Now what's left over if you steal a proton from water? OH. Do you get it? That's the connection. So guys, it turns out that Bronsted-Lowry is saying the same thing as Arrhenius about bases, because our bases will always be in the context of water. So fundamentally, these are the same things. So Arrhenius said bases increase OH. Bronsted-Lowry is agreeing with that, but what he's doing is he's looking not at the hydroxide going up, he's looking at the base stealing the proton from the water that the base is dissolved in, which then gives us the hydroxide concentration, because that's what's left over when bases steal hydrogens. You get the idea? So guys, you're going, holy smokes, this just got really weird. Here's where you're at right now. Guys, fundamentally, these are going to be our definitions for acids and bases. Acids give away protons, bases take them in. But we now have the understanding that these do not contradict these, so long as we understand that all of the acid-base chemistry that we're doing is in the context of water. Does that make sense?
But Bronsted and Lowry can go beyond water.
Yeah, so you
But
can...
at that point, then the Arrhenius definition.
Then good. That's wonderful, Brent. And that's exactly right. That if you were to take Bronsted-Lowry acids and bases, Bronsted-Lowry acids and bases out of the context of water, then these separate. But because all the chemistry we're doing is in water, they stay united. Okay, so then guys, what about this? Now that we understand that water is not a passive participant, it's not passive, it's a participant in the chemistry, do we include water when we're thinking about the chemistry? What did we say? Sometimes. So as we go through this, guys, and this is one of the things you're going to get better at in this unit, sometimes you will include water, sometimes you won't. And you get to pick when you do and when you don't. So when will we include the water? When it makes it better, when it makes it easier, when it makes it clearer. So guys, we'll include water when it's better. We'll not include the water when it's better. We get to choose reflexively when we want to include water. Anna, you okay? Here, do you want some water? Let me bring you some. I do. I know. It's how we roll. So guys, you okay with these ideas? Okay, so then moving forward, the idea then becomes this. We need to now start to delve into this idea of when do we include the water and when don't we. So guys, we understand that Bronsted-Lowry is going to be our informing definition. So now we need to talk about what these protons do. So guys, we understand that acids give away protons. And guys, remember that this is the same as the Arrhenius definition. This is what acids do. They give away protons. The question is, where do they go? And guys, you already know the answer. Remember these guys? Hydronium ion. So if you don't remember, let's talk. So guys, when an acid ionizes into water, the hydrogen ions, which are protons or hydrogen ions, they react with water to form hydronium ion. You learned this last year. Doesn't mean I expect you to remember it. But guys, this is not new. So how does this work? So guys, first thing you got to understand, it doesn't matter what acid we're talking about. This could be hydrochloric acid, sulfuric acid, acetic acid, which is vinegar, nitric acid, which we also used in lab second period. Guys, it doesn't matter what acid we're talking about. All acids give away protons, right? Says who? Bronsted-Lowry and Arrhenius. Guys, that's what acids do, is they give away protons. So now let's ask this question. When do acids give away protons? When they're mixed into water. And guys, don't write this down, but you might find this interesting. Again, don't write it down, but HCl, HF, HI, HClO3, ClO3, HClO4, H2SO4. What are those? I'm missing one. HNO3. These are the strong acids. Guys, in their elemental form, do you know what they are? They're all gases. Guys, they're all molecular gases. So if you get a bottle of HCl, it's actually a tank. It comes as a gas. Guys, at standard temperature and pressure, all of these strong acids are gases. But we don't think of them as gases. We think of them, you identified them as the strong acids. So what do we have to do to these gases to get them to function as acids? Put them in water. And when we put them in water, they dissolve into the water. And when they dissolve into the water, they break. They're strong electrolytes. The hydrogen ions come off. The chloride ions come off. Chloride's a spectator. Where do the hydrogen ions go? They are not free floating in the water. Where do they go? They actually attack water molecules. So guys, when this happens, these hydrogen ions attack water molecules. Now guys, how does that happen? Let's think about it. What is it that would cause that attraction to take place? What is a hydrogen ion? It's a proton with a very strong positive charge. What's it going to be attracted to? These electrons. And guys, literally that's what happened. It's kind of like hydrogen bonding, only it really does form a bond. You've got a naked proton that isn't attached to another molecule. You've got a naked proton that's just this ball of positive charge. You've got these big old lobes of electrons hanging out here, and that proton globs onto one of those lobes of electrons, and when it does, it forms hydronium ion. Yeah.
So the strong acids, those are all bonds.
No, interestingly, no. These are all covalent bonds.
I thought HCl was like
It's not, no. So, and this is interesting. So, and we're going to look at this in 2 class periods. It turns out that all of these, oh gosh, that's not funny. All of these bonds that exist between the hydrogen and whatever they're bonded to, they're all covalent bonds. But the thing that's interesting is they're right on the cusp of ionic. Like the bond that exists between hydrogen and fluorine is the most polar possible covalent bond. If it were even a little bit more polar, we would think of it as being ionic. So it's right on the, wait, that's not HF, that's HBr. Never mind. That's the wrong. No, that's HBr. HF is a weak acid. So, but these bonds are right on the cusp of being ionic, but they're not quite there. Okay. So guys, understand then this idea. We understand that this proton then attaches to hydrogen and or to water, and it forms hydronium ion. Now, which one of these acids does this? All of them. But guys, it doesn't stop there, because not only do the weak acids or the strong acids do this, so do the weak acids. So if you take vinegar molecules and dissolve vinegar molecules in water, it breaks right here. These hydrogens attack water and form hydronium ion. So guys, all acids form hydronium ion in water. Get the idea? Okay, you may find this is sort of an extra thought, but it's interesting. So guys, what about vinegar? You now know that the strong acids are gases in their molecular forms. What about the weak acids? If you could get, they're actually crystalline solids. So guys, acetic acid, which is CH3COOH, when it's not dissolved in water, it's actually a solid. So almost all of the weak acids are crystalline solids that you then dissolve in water to make acids. So, you guys getting the idea? Yeah.
Are there any acids that just come in a liquid form without being in water?
No, not given these definitions. When you get into second year chemistry in college, organic chemistry, you'll find out there's a third way to define acids and bases. And that's the Lewis definition of acids and bases, where you're actually, instead of looking at hydrogens, you're looking at electrons. And when you open up your reach to just talk about electrons, then there are a lot of liquids that are acids and bases, but not in these definitions. We have to think of them as being in water. Okay, so guys, with that said then, let's talk about how we're going to handle this. So you guys are okay with this chemistry, right? Acids give away protons, they attack water, they form hydronium, yes? Okay, so guys, here's the trick. This hydronium ion then is the stuff that causes acids to behave the way they do. So if you spill sulfuric acid on your arm and you're sitting there whimpering as it burns a hole in your arm and you're going, ow, 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 sulfuric acid is burning me. No, it's not. Sulfuric acid does not burn. What is it that's actually burning your flesh? Hydronium ion. Guys, this is the, if you will, active ingredient in acids. Sulfuric acid, H2SO4, is not dangerous. It only becomes dangerous when you put it in water. It gives away hydrogens to form hydronium ion, and it's the hydronium ion that's the corrosive stuff. But guys, it's also the stuff that makes orange juice tart, because citric acid also gives away protons to water to form hydronium ion. So why can you drink orange juice and you can't drink sulfuric acid? It's the amount of hydronium ion that they make. Citric acid doesn't make much hydronium ion, so we can drink it and interact with it. But guys, sulfuric acid makes more hydronium ion, and as a result, it becomes dangerous. Yeah.
You think about it almost like concentration.
Not almost, exactly. It's a concentration issue. Now understand, with that said, the other part of the molecule, like the sulfate in sulfuric acid, can also do chemistry sometimes. If you've watched Breaking Bad, you may know examples of that. But guys, understand that it's really the hydrogens. Did you guys see that Breaking Bad episode where Walter had his little accomplice get rid of a body by throwing it in a bathtub full of hydrochloric acid, and it never mind. All right. No? Okay, what? Similar idea. All right. So guys, this then is the question. How are we going to represent this chemistry? How are we going to represent what's going on right here? Well, guys, there's two ways that we're going to do it. So one of the ways that we're going to do it is this. We're going to, and just write this down with me, we're going to say that acids produce hydrogen ions. So we're going to say something like, if we've got a bottle of HCl, we've got a bottle of hydrogen ion. But guys, is that really true? If you pick up a bottle of hydrochloric acid, is there any hydrogen ion in there? Where'd it go? It bonded to water to form hydronium ion. So guys, understand, when you pick up a bottle of hydrochloric acid, there is no hydrogen ion in there because all the hydrogen ion is bonded to water to form hydronium ion. But here's the thing that's weird. We're going to use these two interchangeably. So what logic allows us to do that? So when we pick up a bottle of hydrochloric acid, we can think of it as being a source of hydrogen ion, or we can think of it as being a source of hydronium ion. And guys, we are going to use either one of those interchangeably, but they're not the same. So what makes them interchangeable? Exactly. All acids have to be dissolved in water. So guys, we understand that that's really not what's in the bottle. A hydrochloric acid solution does not contain hydrogen ion. It forms hydronium ion. But because we know that has to be the case, it's simpler for us to just use hydrogen ion, understanding all the while that it's really hydronium ion. So guys, we're going to use this interchangeably. So now you're going, wait a second, what are you talking about? Guys, this is that whole thing that I was sharing with you earlier where I told you sometimes we're going to include the water and sometimes we're not. So if we do include the water, we'll understand that acids contain hydronium ion. But because we know they have to contain hydronium ion, sometimes it's going to be easier to just do this, and you get to pick which one you want to do. Do you get the idea? You okay with the interchangeability idea? Okay. So guys, with that said, we're now ready to dig a little bit deeper into Bronsted-Lowry acids and bases. Do you remember conjugates? Should we go over it? Let's go over it quick. So guys, when acids and bases react, what they do is they form new acids and new bases. So let me explain to you what we're talking about. The chemistry looks like this, and you may want to write this down. So we've got an acid reacting with a base. And you know what? Let's for now, this doesn't need to be equilibrium, and it may be distracting. It could be equilibrium, but it doesn't have to be equilibrium. So let's just make it not equilibrium for now, and then we can think about it as equilibrium later, because it works in either context. So guys, I think what I'm going to do, and this isn't in the notes, but I just want to give you an example and see if this example drives home the idea. So let's do this. Let's go HCl. You're going to want to do this with me. And NH3. So guys, what is HCl? Acid or base? Acid. NH3, would you guys have known that's a base? NH3, it's ammonia. It contained, did we talk about the idea that things that contain nitrogen tend to be bases? We'll talk about that later. For now, just understand that it's a base. Yeah. So guys, now let's talk Bronsted-Lowry. What do acids do? Give off hydrogens. What do bases do? Take them in. So write the products. If acids give, not if, they do. Acids give away hydrogens, bases take in hydrogens. Predict the products. Did you get it? So guys, let's take a look. So if the acid gives away a hydrogen, what's going to be left? Cl. But if you wrote down Cl, it's wrong. Cl minus, because the proton is positive, so the thing that's left over has a negative charge. Now guys, where did the proton go? It didn't go away. It went to the NH3, and that formed NH4. But if you wrote down NH4, it's also wrong because it's positive. So guys, what we formed is chloride ion and ammonium ion. So now let's talk about conjugates. So here's the idea. When the acid lost a hydrogen, what did it turn into? Chloride. That is what is called the conjugate base. So it's the conjugate opposite thing. So that would make it the conjugate base. Now guys, go to the base, and the base took in a hydrogen and it turned into NH4. That makes it the conjugate acid. So guys, when they form conjugates, they trade roles. So the acid becomes the conjugate base, the base becomes the conjugate acid. Go ahead.
So NH3 is a weak base.
Correct. Yes.
So if you have a greater amount of HCl,
Mm-hmm.
not all the NH3 molecules are going to accept the hydrogen.
Correct. Right. And
So you'd end up with the rest of the HCl still get rid of the hydrogen and create hydronium.
exactly, precisely, yes.
All the HCl is still.
Yeah, and so Talmadge, I don't want to run this down too far, but this is actually not what this chemistry does. What actually happens is this hydrogen goes to hydronium and then goes to NH3. Because in order to put these things together, you would start with hydrochloric acid, and that acid, because it's dissolved in water, would have already formed hydronium, and then the hydronium, when you dump them together, would release the hydrogen to NH3. So, but that said, so guys, let's talk about conjugates now. So here's the idea. What does it mean if we focus our attention over here? What does it mean to be a conjugate acid and a conjugate base? Are they really acids and really bases? And the answer is absolutely. So guys, these function as acids and bases. So if this is an acid, we call it the conjugate acid, but if this is an acid, what's it going to do? Give away a hydrogen. And where will the hydrogen go? To the conjugate base. So if this gives away a hydrogen and gives it to the conjugate base, what do these then turn into? Those, and the reaction then goes in both directions. So the idea here, guys, is this conjugate acid can then give away a hydrogen to the conjugate base and push the reaction in the other direction. So guys, conjugate acids are acids, and conjugate bases are bases, and these can then react together and form the original reactants. And we're going to talk more about that later, but that's the idea behind conjugates. We're going to do a bunch of conjugate chemistry this year, and the idea is that the conjugate acid, which is formed from the base, and the conjugate base, which is formed from the acid, very much can function as acids and bases and do chemistry in the other direction. Yeah.
So there, I've always been slightly confused as to how the hydronium actually functions within the entire equation. That's something that we're going to
Oh, a lot of time. Yeah. Mhm.
now.
Yeah, a ton of time. No, and yeah, we're gonna wait on that one. So guys, let's do this then, and let's maybe look at a couple other acid-base conjugate ideas. So take for example this. You know what? Let me switch to red so it stands out. So let's go HCl. So guys, do this with me and figure out the products. HCl reacting with water. Oh yeah, not necessarily. We'll talk about it, but I don't think you have to write it down. And then guys, while we're at it, let's do this. Let's do one other. Do that one too. So guys, let's look at these products. So we know that HCl is the acid. So HCl is going to give away a hydrogen, and it will form chloride, and it will form hydronium. You okay with that? So now let's do our conjugates. Here's our acid, here's our base. So what is chloride? The conjugate acid or the conjugate base? The conjugate base, because it's the acid minus the hydrogen gives us the conjugate base. So what does that then make hydronium ion? Conjugate acid. Is that okay? Okay, so now let's do this one. And so guys, now we come down here. This gives away a hydrogen. So we get CH3COO. And then again, we form hydronium ion. So now let's talk about our conjugates. Guys, this is acetate, right? What is the acetate ion? The conjugate acid or the conjugate base? So go to the acid, take away the hydrogen. What's left is the conjugate base. So that would make acetate the conjugate base, and that would make hydronium ion the conjugate acid. Is that okay? Hold on a second. Is that okay? You understand the idea? Now we need to talk, because I'm going to lead you to a very important thought. Guys, one of these equations is not written properly. Which one? Why the bottom one? What's wrong? It's a weak acid, so how do we fix that? It goes this way. So guys, the bottom one is a weak acid, so it reaches equilibrium. What about the top one? Does that one go both ways? Guys, make sure you're clear on this, because you're about to have an aha moment. The bottom one goes both ways. How do we know? Because it's a weak acid. Does the top one go both ways? How do we know? Because it's a strong acid. So guys, you've never even thought about this, but now it's time to talk about it. Why? Why is HCl a strong acid, and why is acetic acid a weak acid? You ready for the answer? It's really neat. Check this out. So HCl gives away hydrogens to water and it forms hydronium ion, right? Does it go the other way? It doesn't. How do we know that it doesn't? Because it's a strong acid. Why doesn't it go the other way? And guys, the answer is this. Chloride ion is a worthless base. Chloride ion, the conjugate base, is worthless. Now guys, we live in a more politically correct world than that, so the word that we use from the textbook is negligible strength. That means worthless. So guys, it turns out that chloride ion is a worthless base. Chloride ion has absolutely no ability to steal the hydrogen back from hydronium. Consequently, it cannot drive this reaction in the other direction, and it stays over here. So the reason that it stays over here is because chloride is a worthless base. But guys, what about acetate ion? It is actually basic. Guys, acetate ion is able to take hydrogens away from hydronium, drive this reaction in the other direction, and force it to reach equilibrium. So now let's have this conversation. Why is acetic acid a weak acid? Why is acetic acid a weak acid? Because acetate ion is basic. Do you see it? Do you get the idea? So guys, let's go through this again. Hydrochloric acid is a strong acid, yes? What does that mean? It means it completely breaks apart and it never goes back. Why is that true? The answer is because chloride is a worthless base. It cannot take in hydrogens from hydronium, and it doesn't go backwards. Now, guys, when we think about acetic acid is not a strong acid. It is a weak acid. Why is acetic acid a weak acid? And the answer is right here. The reason that acetic acid is a weak acid and not a strong acid is because acetate ion is basic. this conjugate base actually is basic, and the conjugate base can steal hydrogens from the hydronium, push the reaction backwards, and force it to reach equilibrium. Just a minute. So guys, the important thought then is this. The conjugate bases of all the strong acids are worthless. Does that make sense? The conjugate bases of all the strong acids are worthless. The conjugate bases of all the weak acids are basic. Do you need to write it down to make sure you can keep track of it? Does that make sense? So the conjugate bases of the strong acids are all worthless bases. The conjugate bases of the weak acids are basic, causing them to reach equilibrium. So guys, I'd love to answer questions, but we got to keep them on point. Go ahead.
So this is because so chlorine is not, doesn't have enough chemical, so chlorine's charge is by there, or what's
Yeah, so what is it about chloride that makes it worthless? We're going to answer that in 2 class periods. Yeah, we're going to get into it. It's not a simple answer, but we're going to talk. Yeah, it's actually a crazy big answer, but we'll talk. Other questions or things? You okay with these ideas? Okay, so guys, what we're going to do then is we're actually going to summarize this in an even bigger statement. So here's where we're at. We're okay with the idea of conjugates, right? But this is the important rule. This is the stuff you need to make sure you're clear on. Guys, strong acids and bases form worthless conjugates. Again, we don't use the word worthless. We use the word negligible. And then, guys, the weak acids and bases have conjugates that actually function as conjugates. So the stronger an acid is, the weaker its conjugate base is. And the stronger a base is, the weaker its conjugate acid is. But you're going to find out, guys, it's a sliding scale. Hi. There you go. Thank you. Bye, you guys. You okay with the idea? Anything you want to explore there? Or are you good? This is going to be an important idea, guys, and we're going to flesh this out more throughout the unit. But for now, what we understand is strong acids have worthless conjugate bases, and then if it's not strong, if it's weak, there's a sliding scale between how weak the acid is and how strong its conjugate base is, and we'll get more into that later. You okay with the fundamentals, though? Okay, so now, guys, we're going to go into this idea of these relative strengths. So the idea then is this, and I think you're comfortable with this, but I'm going to show it to you graphically. So the idea is this. What is a strong acid? Not what are they, but what do they do? What makes an acid a strong acid? Completely ionizes in water. So guys, a strong acid completely transfers its protons to water. Now guys, what do you now understand about why? Why is it that strong acids completely transfer their protons? Why is it this happens completely? It's all about the conjugate base. What do you now know about the conjugate base of a strong acid? It's worthless. So guys, the acid gives away the hydrogen. The conjugate base can't take it back. So they completely dissociate. So guys, these are the set, you know them, right? So then what about the weak bases? Well, or the weak acids? Guys, weak acids only partly ionize in water. And again, why is that true? Because their conjugates can function as bases, and as a result, they can take these protons back in. So this then brings us again to this relationship between the parents and the conjugates. And guys, fundamentally, and we already wrote this down, but I want to show it to you graphically. Remember, the idea is this. The stronger the acid, the weaker the conjugate base. And that works in all different directions. The weaker the acid, the stronger the conjugate base, and it works for bases. The stronger the base, the weaker the conjugate acid. They all fit together inversely. And I'm going to show you a picture of it in just a second. Can I show you? So guys, it looks like this. This is interesting. Let's do this. All right, so guys, here we go. Well, actually, you know what? I want to be able to draw in here. So I still think I can draw in here when I do this. So guys, let's take a look at this and see what sense we can make of it. So guys, notice the acids that were given up here. HCl, H2SO4, and HNO3. What do we know about those three acids? They're strong acids. So if those are strong acids, what do we also know about their conjugate bases? They're worthless, but unfortunately we don't use the word worthless, we use the word negligible. Okay? Then guys, if we look at the other end of the spectrum, this is interesting. These are all substances. Whoa. How'd that? Oh, I think I touched it. So guys, these are all substances that can actually act as strong bases, which means they completely take in hydrogens. But then guys, if you come over here, look at the strengths of their conjugate acids. Those are also negligible. So this works on both ends of the spectrum. If you've got a strong acid, its conjugate base is worthless. If you've got a strong base, its conjugate acid is also worthless. But now, guys, we get into this interesting region in between, where we've got all of these substances that are actually acidic. But of them, HSO4 minus is the most acidic, and HPO4 minus is the least acidic. But now, guys, look at what happens to their conjugate bases. Their conjugate bases go in the opposite direction. So if this is the strongest weak acid, this is the weakest conjugate base. And if this is the weakest weak acid, then this is the strongest conjugate base. So guys, there's an inverse relationship between the strength of the parent and the strength of the conjugate. And remember, the strongs are the ends of the scale. If you've got strong, you've got worthless. If you've got strong, you've got worthless. But in the weak combinations, the weaker the acid, the stronger the acid, the weaker the conjugate, the weaker the acid, the stronger the conjugate. Do you kind of understand the idea? Okay, so guys, we're going to be using that throughout the year. And again, I told you, some of this was going to sneak up on you as being new. Understand, we're laying groundwork right now. So if you have a general sense of this idea of relative strengths, you're right where you need to be. So you guys okay? You're good? Okay. So now, gang, we're going to move forward into something that's also new. And we're going to get into this idea. Well, maybe we should do this first. Are you guys okay with identifying conjugates? Do you understand the idea of amphoteric, which means it can be either one? You okay? Okay. So now let's do this. This is, guys, well, let's see how we do. We may end the day here. Let's see. We'll see how we do. So, guys, this is really interesting. You ready? You want to get this in your notes. This is called the autoionization of water. So guys, maybe we jumped through this too quick. Let's make sure we're okay. You know what? I'm going to make sure we're okay by going back a slide. We may, you better understand this. So guys, looking at these two reactions. What is water doing in this reaction? Is it gaining or losing a hydrogen? Gaining, right? Because it's turning into H3O. So what does that make water? An acid or a base? Base. So now what's water doing in this reaction? Losing a hydrogen, we can tell because it turns into OH. So what does that make water? Makes it an acid, right? And so the question then becomes, which one is it? And we understand that it can be both, and we call that amphoteric. But guys, it brings up an interesting question. What if you have just a cup of water? What if you have a cup that only contains water molecules. Because it turns out the water molecules react with each other. When these water molecules run into each other, at any given moment, some of these water molecules can behave acidically, and some of these water molecules can behave basically with each other. We call this the autoionization of water. So guys, fundamentally the idea is this. Because water is amphoteric, it actually has the ability to ionize itself. Here's what I need you to do. Write the balanced equation for what this process would look like.
We're using like E1 and 10.
We'll talk, hold on, you can't steal the thunder, because that's the interesting part. That's the part that's cool, and it may be where we end the day. So guys, write the balanced equation for this. What does it look like when water reacts with water as an acid and base? Did you get it? Did you get this? Guys, that's the reaction. When this happens, a water molecule reacts with another water molecule. One acts as the acid, one acts as the base. One picks up a hydrogen and forms hydronium. The other loses the hydrogen ion and it forms hydroxide. You get the idea? So here's then the next thing we need to do. Write the Kc expression for this. Do it in your notes. Be careful. Maybe I shouldn't have said that. Too late, I already did. And did you see the double-headed arrow? It's equilibrium, right? Imagine if it wasn't. It'd be a crazy world. If there was no water on Earth, if it all existed as hydronium and hydroxide. That'd be a great premise for a book. If like aliens zapped our planet with a ray gun that caused all the water to ionize.
I don't know how big the market is for that.
For the ray gun or the book?
The book.
Oh, the ray gun.
The ray gun kills everybody.
There's a very real chance that our Pentagon has such a weapon. So guys, Kc expression looks like this, right? Kc is equal to products divided by reactants. Our products are hydronium and hydroxide and water, and there's two of them, and so we'll just square it. Good? Bad. Why bad? Not good, bad. Why bad? Let's put subscripts on it. Liquid, liquid, aqueous, aqueous. Yeah, remember guys, we do not include, this is heterogeneous, we don't include pure liquids or pure solids in our Kc expressions. So, guys, it turns out that this is the Kc expression for the autoionization of water. But we don't call it Kc, we call it Kw. Grab your AP sheet. You like how I condensed that? Thank you. So guys, it is 1, 2, 3, 4, 5 equations down. Kw is equal to hydrogen times hydroxide. Compare that to what's on the board. Hydrogen times hydroxide. Why is that different from what we put on the board? Because they're included. Exactly. See, we wrote hydronium because we were looking back at the original chemistry, but they dropped off the hydronium and just called it hydrogen. But we're okay with the idea that those are the same? Okay. Oh, yeah, absolutely. Yeah, better to use the one on the equation sheet, but you can use either one. But guys, here's the thing that's interesting. It's on the slide and it's also on the equation sheet. Guys, you can actually study water and you can figure out the Kw value for water. the kW value for water at room temperature at 20 Celsius is 1 times 10 to the negative 14th. Do you see where that is on your equation sheet? Do you get it? Do you get it? Do you get it? Guys, check this out. You could write this down with me if you'd like. Oh, for the love. Oh, good. So guys, KW do this in the most unobtrusive way you can, Matt. This is not going to work if we're going to do this for the rest of the year. Okay, I can't, because you walked through the door like you were looking for a fight. So guys, 1 times 10 to the negative 14th is kW, right? Now guys, check this out. That is equal to these two things. But think about this. What do these two things have to be? The same. Does that make sense? That every time we form a hydronium, we form a hydroxide, yes? So those have got to be the same. Let's call them X. So if we call those X, this is X squared. If you then solve that for X, can you do that in your head? What's the square root of this? 1 times 10 to the negative 7th. Now do you get it? That's why water has a pH of 7. Because guys, pH is the negative log of hydronium ion concentration. The hydronium ion concentration of water is 1 times 10 to the negative 7th. Take the negative log of that, and the answer is 7. This is why water has a pH of 7. The reason water has a pH of 7 is because at any given moment, the molarity of hydrogen ion is 1 times 10 to the negative 7th. And we know that because we can work this backwards, understanding that hydronium and hydroxide have got to be the same. So this is the fundamental reason that water has a pH of 7, because the molarity of hydronium ion is 1 times 10 to the negative 7th, as given by this relationship. Go ahead.
So I also see a 14, and I don't know, is that just a coincidence, or is 14 usually where we base it?
No, it's not a coincidence at all. And so yeah, we've got a 14 here, which is the upper limit of basicity. And the reason is this. KW, and this is what we're about to talk about, guys, KW doesn't change. It's a constant, right? Didn't we say that K values don't change? Right? So the K value is a constant, which means if we take this bucket of water and if we dump in something that's basic, that will increase the concentration of hydroxide, which will then force the hydronium ion concentration to drop. So guys, it turns out that if we adjust one of these by adding an acid or a base, as one goes up, the other goes down to maintain the value of KW, to maintain the equilibrium. So it turns out that when this reaches a minimum somewhere around 0, this would reach a maximum around 14. Yeah, so and that's the way we're going to deal with this is, guys, this equation doesn't just allow us to have that magic moment when we figure out that pH of water is 7. It's actually something that will allow us to figure out either one of these numbers given the other. And that's where we're headed with this. So guys, join me and let's wrap up with this. So guys, this relationship KW does not only hold true for water. It also works for acidic and basic solutions. So it really becomes a seesaw. That's the way I think about it. That KW is our fixed point. So if we think about this as being a teeter-totter, as one of these goes up, the other has got to be going down in order to maintain the value of KW. So if we know the concentration of hydrogen ion, we can figure out the concentration of hydronium ion, and vice versa, because one interacts with the other to maintain KW. So guys, the question then becomes this. how do we figure out the concentration of hydronium ion? How do we measure it? Guys, we're going to do this in lab. How do we measure the concentration of hydronium ion? You already know the answer. pH. Guys, pH is the concentration of hydronium ion. Do we need to go over it, or do you remember the math? Do you remember this? That pH is the negative log of hydrogen ion, but it's also the same as the negative log of hydronium ion. You okay with that idea? Okay. Let me think here. I think we'll be okay. So guys, what then is pH? So guys, pH is just an expression that gives us the strength of an acid or base. Remember, low pHs are acidic, high pHs are basic, right? And this will then let us study water-based solutions. So let me show you what I'm talking about. Check this out. So guys, this is really interesting. You're going to learn a lot from checking this little thing out. You know what, maybe zooming wasn't the best idea because I want to be able to write on this as well. So guys, well, I'll do this and then I'll stay red and then we'll go up here. Okay, so guys, let's start down here at the bottom of the pH scale, which is stomach acid, which has a pH of 1. Guys, what does that mean that stomach acid has a pH of 1? Well, if stomach acid has a pH of 1, that 1 is the exponent in the molarity, right? So that means that the hydrogen ion concentration then of this is actually 1 times 10 to the negative first. So if we look down here, a pH of 1 means the hydrogen ion concentration is 1 times 10 to the negative first. What if we go up here to, let's say like tomato juice? Guys, tomato juice has a pH of 4. So what's the hydrogen ion concentration? 1 times 10 to the negative fourth. Then your spit is about pH 6, which means it's got a hydrogen ion concentration of 1 times 10 to the negative sixth. Now guys, the thing that's interesting though is that look what's happening to the hydroxide ion concentration. So they're also giving us hydroxide ion concentration. So if the pH is 1, that means this is the hydrogen ion concentration. But we could go Kw is equal to hydrogen, is equal to hydrogen times hydroxide. And by using that equation, we could then figure out the hydroxide ion concentration, and that would have to be 1 times 10 to the negative 13th in order to maintain that idea that it all comes together at 1 times 10 to the negative 14th. But then, guys, they do this interesting thing. Not only can we talk about pH, we can also talk about POH. In the same way that we can take the negative log of hydrogen ion, we can also take the negative log of hydroxide ion, and in doing that, the pH of this, or the POH of this, is 13. So let's do that again up here. So guys, let's go tomato juice. Tomato juice has a pH of 4. So its hydroxide ion or hydronium ion concentration is 1 times 10 to the negative fourth. Using the equation, we know the hydroxide ion concentration is 1 times 10 to the negative 10th. But then if we take the negative log of that, the POH is 10. But guys, look at how this tracks. pH of 6, POH of 8. pH of 10, POH of 4. Do you see the relationship? What do the pH and POH always add up to? 14. Find it on your equation sheet. Do you see it there, guys? It's the third from the bottom. pH plus POH is always equal to 14. The reason is because hydrogen ion times hydroxide ion is always equal to 1 times 10 to the negative 14th. So guys, now what we've got is two interesting equations that we can use to jump between all of these values. So we've now got this idea of POH and this idea that pH plus POH is equal to 14. So not only can we figure out pH values, we can also figure out pOH values, and we know that the two of those will add to 14 because of that seesaw around KW. Was that a pant load of stuff? Pant load of stuff. So guys, these are all the foundational relationships that we're going to use throughout this unit. I know that right now you're going, oh my gosh, my head is swimming. We've got autoionization, we've got conjugates, we've got weak, strong, we've got pH, pOH. Guys, here's what we're going to do. We're going to let the homework sort of be the guide. So guys, this is your homework assignment. Yeah, it's big. Guys, the way to know whether or not you really understand what we just covered is to go back and to go over the homework. So when I see you on Thursday, we're going to spend time. We're going to make sure that you understand the answers to these questions. Guys, the assignment is not as big as it seems. Many of these questions are very simple calculation-based problems. But guys, with that said, understand your homework in this unit is going to become greater. You're gonna see your homework load go up in the next couple weeks. Not significantly. I've never had anybody drop the class as a result. But guys, understand your homework load is going to increase over the next few days. So we'll do this. We'll look at this on Thursday, and then guys, we'll move on from there. Let me do this while you're getting this written down. First, let me stop recording.